we're going to take a look at one last physical application example of integrals, and it's with these pumping problems or lifting problems. Our goal is that we want to find the work required to pump some liquid out of some tank. So this is again a work problem that we had. We remember from before that work is the product of force and distance. So what we have to do is figure out what kinds of forces are at play and what's our distance going to look like if we have some sort of a body of liquid that we're trying to pump out of some sort of container or tank. So you may remember from some physics classes that force is mass times acceleration. And in this case, we're going to be lifting our stuff upwards, and so our acceleration is gravity. We might also remember from earlier that mass is density times volume, and in our case earlier when we were thinking about the thin wire, we were able to take that three-dimensional volume and condense it down to a one-dimensional measure of length, and then when we did all of our Riemann sums, that turned into delta x. That may not be the case here. We're going to be still looking at a three-dimensional measure of size, volume. So our work is really force times distance, yes, but since force is actually mass times gravity, and our mass is actually density times volume, we have density times volume times gravity times distance. That's really what work is. Now we can see what the issue, or maybe issues, are going to be here. There's two issues that I can see right off the bat. The first is that distance, capital D, is variable. If I have some sort of a container and there's water in it or some other liquid, this water has a shorter distance out than this water. I have to pump the stuff at the bottom of my tank the whole distance up the tank, whereas the stuff on the top of the water, I only have to pump a little bit to get out of the tank. So there's this variable distance. I got to delete that terrible drawing. There's also possibly a variable volume. Maybe we have some sort of a cone type tank, where down here, the volume might be a little bit different than up here if we look at just regions of this thing. So this might be a little bit of an issue as well. So we have to take into account these two types of variations we can have. Notice that with liquid, we don't have the problem of variable density, because you might remember that if you put in liquids with varying densities and try and mix them together, they will separate. And so what happens is you end up with some sort of a tank like this, and you have one liquid on the bottom, and then stacked on top of it is another layer of a different liquid, and maybe you'd have three different layers. So you have these discrete sections, right? These breaking points where we don't actually change liquids continuously. We just kind of start and stop. So what you can do is cut this in to three problems and just consider each of these regions separately. And that works out nicely. So we don't have to worry about variable density. All right, so what we're going to think of is using that slice and sum strategy. I have a nice picture of a tank here that we'll draw on so we don't have to worry about my terrible pictures. And we're going to slice this up into some horizontal slices. So I'm going to take a slice right there. We'll take this little, in this case, circular shape, and we'll take it out, and we're going to just consider this little bit. Now, inside of this is a bunch of water, or whatever other liquid that we have, right? This isn't some metal disc or whatever. This is actual liquid inside of this little slice. And we want to say for this slice, we need a bunch of stuff. We know that work is going to be a product of a whole bunch of different things. So remember, work is our density times our volume times, so that's our mass, times our acceleration due to gravity, times some distance. Density and gravity we don't have to worry about. Those are going to be constant. We can look up the density for whatever liquid we have. We can look up the acceleration due to gravity if you don't remember it. We have to figure out what's the volume and what's the distance. The volume, we already have figured this thing out. We know that that's going to be the area of the cross-sectional face times the really small thickness. I'm going to call this delta y, and if we take a look at this thing flipped over here, we can come up with the area of its face. So if we have some area function, we can multiply it by delta y to get volume. Cool. So we'll say V sub k, the volume of the kth slice, is going to be A of y sub k star. We're going to pick a random point in this thing to grab the area of the face from. We'll multiply it by delta y. There's our volume. Our distance for this thing, what we'll notice is that the distance is whatever the distance is from the top of my tank, assuming I'm pumping it out of the top, or whatever nozzle that we have. Maybe it's here, whatever. But the distance from that point of exit down to the layer that we have. That's just a difference in y values. We can call this h for the height, and this is going to be our y sub k star. So distance is really going to be a function of y, and it's going to normally be h minus, well, I'll leave it not as a function for now. I'll say distance is h minus y sub k star. So what that means is that the work for the kth slice is going to be rho for density, g for gravity. Then we need our volume. So I'll say A of y sub k star times delta y times our distance, which is h minus y sub k star. I'm going to rearrange this so that my delta is at the very end, because it makes me a little bit nervous to see that written in the middle of all this stuff. Notice now that we can find the approximation of the total work involved by just adding up the work for each of these slices. There are a lot of pieces to this, but we can track all these back to this formula here, which, remember, this is really force times distance. And then what we can do is our classic example of tossing a limit onto this and getting an integral. So we're going to take a limit as n goes to infinity. So you'll think of infinitely thin slices of this liquid. And we'll add up all of the work required to move each of those really thin slices. And if we can do that, and if this truly is a Riemann sum, which it is, function, well, a combination of functions, but we could write this as a function of a single y value that we've picked for the kth subinterval times delta y. We're going to get an integral from our bottom, I'll call this C, up to not the top of the tank, but up to the top of our liquid, D, of rho times g times our area function times h minus y dy. Now sometimes this is left as a more general d of y function, but for the most part our distance is really just going to be a difference of the exit point y value and the y value of the slice. So here's our pumping problem formula. The work required to pump or lift some liquid with density rho, some distance, d of y, in a tank, or out of a tank, we can say, with cross-sectional area a of y, from y equals c to y equals d. This is the limits of our liquid. So this is the bottom of the liquid. Oops, that's a g. And this y value is the top of the liquid, is this formula that we have here. We can factor out rho and g since they're constants. Remember, density has to be constant here because these are liquids. They'll separate if it's not, and then we can consider it all separately. And then c and d would be the limits of that layer of liquid. And g is a constant because gravity is constant. And so we really just have this product of the area function and the distance function. But again, normally this distance function is just h minus y, where h is the y value of the top of the tank, or if you want, you could say, or the nozzle that we're pumping out of. That way, if you have some sort of a tank that's set up like this, where your nozzle isn't all the way at the top, then we'll just take a look at this y value here. Cool. So what we should do is at least take a look at one example. So we're going to go back to that frustum shape, and we're going to consider a tank that is 2 meters tall, with a bottom radius measuring 3 meters and a top radius measuring 1 meter. And we're going to say I don't want to say it's half full because I don't want to say that half of the volume is there. I just mean it's filled up to the halfway point. So it's filled up like a meter tall, right? If it's 2 meters tall total. And we've got some unknown liquid, who cares, but it's got a constant density rho. We want to figure out how much work is going to be required to pump this liquid all the way up and out. So let me just draw on here what we have. I'll do this in blue. This bottom radius, actually, you know what? I've got my straight line tool. Let me do it. That bottom radius and that top radius we know. So for this top one here, we've got that r is equal to 1. And on the bottom, we have that r is equal to 3. We also know the height of this. It's 2 meters. And we also know the height of our water, or I shouldn't say water, our unknown liquid that we have. This is 1 meter. And I'm going to get rid of my units because I don't really need them here. Don't tell the scientists. All right, so this is the stuff that we've got. We get to label y values. Sometimes it's reasonable to pick things to be certain y values. I normally set this thing on the x-axis, and so I'll make this a y value of 0, and this a y value of 1, and that means the top is a y value of 2 in this case. You don't have to orient it like that. You could start at a y value of 7 and go up to a y value of 9 at the top of our frustum, but it doesn't really make a lot of sense to do that. So we've got those limits of integration. We're going to go from 0 to 1, and we also have our distance. It's going to be 2 minus y. So let's just start writing this down. Our limits of integration, c is going to be 0, and d is going to be 1. And our distance function is going to be 2 minus y. So all we need now is the area function. We can see pretty clearly that the area function is going to be the area of a circle. Because if we take a look at a cross-section of this thing, if we just take a really thin slice of this and pull it out, we're going to be looking at a really thin disc-looking shape. And if we put that on its face, that's going to be a circle. We've got this little delta y right here. So we just need to know the area of that circle. That's not hard if we know what the radius is. But what we'll notice is that our radius is going to change, right? Our radius changes from 3 up to something else. We'll have to figure out what that's going to be. And that means that our area function is going to be variable. So you can do a whole bunch of different things. What I would like to do, maybe, is to just see if we can draw some things. I'm going to draw a set of axes, and I'm going to draw the edge of my frustum. Let me move this down here. So at a y value of 0, my radius is 3. So I have this point right here. And at a y value of 2, my radius is 1. So if I just connect those dots, this is the function that defines the outer edge of my frustum, and thus is going to define my radius. My radius is this distance right here. That is an x value. So what you'll notice is that we need a function that spits out this x value for a point on this line given a y value. We can come up with the linear function defining this line pretty easily. You can either use point slope form, or we can keep tracing our line back and find a y-intercept or whatever. Either way, hopefully we can see that the slope of this is -1. And then if you want, you could use this point 1, 2. That'll work. And we can go ahead and toss this into our equation of a line in this point slope form that we've used ages ago. And we end up with -x plus 1 plus 2. So that's y equals -x plus 3. But remember, we wanted to be able to plug in an x value and get out a y value. So what I'm going to do is add x to both sides and subtract y from both sides. And what I've got is that x equals 3 minus y. Now, that's not my area. That's my radius. So r is equal to that thing. So then what we can do is say, if we know that this is our radius r, then we can find area very easily by just saying pi r squared. Let's move to the next slide because we're running out of room a little bit. So I'll try and keep track of the things that we know already. Let's do this. So we had that c was equal to 0 and d was equal to, 1. We also had that our distance function was 2 minus y. And then we had that our radius was, I forget, was it 3 minus y? Yeah, that's right. Okay. And we had this circle. Let me try that again. There we go. We had this circle with a radius of r, and we wanted to find the area. A of y is pi r squared, so that means it's pi times 3 minus y squared. Or we can say pi times 9 minus 6y plus y squared. That's our area function. All this to say, we can set up our integral for work. It's the integral from 0 to 1 of the density times our volume. I'm just going to use the area here because my differential is going to go in at the end, times acceleration due to gravity, times our distance, and then there's our differential that multiplies by that area to get volume. What you'll notice is that you can pull a whole bunch of stuff out. Pi, rho, and g all can get factored out. And now I've got an integral from 0 to 1 of 9 minus 6y plus y squared times 2 minus y dy. You can multiply all of that. Oops, let me pull my coefficients out, and then I'll think about that multiplication. Pi times rho times g, integral from 0 to 1 of, okay, what do we have? Our constant term is going to be this 9 times 2, so we have 18. Then our linear terms are going to be the 9 times negative y and the negative 6y times 2. So what's that? Negative 21y. Our quadratic terms are going to be a 2y squared plus 6y squared, so that's an 8y squared. And our cubic term is going to be just the y squared times negative y, so minus y cubed dy. And then this should be pretty easy to evaluate. You're going to get pi rho g times 18y evaluated at 1, that's 18, minus 21y squared over 2 evaluated at 1, so that's going to be minus 21 over 2, plus 8y cubed over 3 evaluated at 1, so that's plus 8 thirds, minus y to the 4 over 4 evaluated at 1, and that's 1 over 4. And you'll notice the rest of the stuff evaluated at 0 is all 0. So you can go ahead and figure out what this is. I think I did that one already. I think it's 119 over 12. So this is 119 pi rho g over 12. Something like that. So that's a lifting problem or a pumping problem. The things that we can change, mostly the shape and size of the tank. That's mostly what we're going to be impacting here. So if you have a tank that's not set up as a frustum, then maybe your cross sections are going to look a little bit different. Maybe you have rectangular cross sections. Maybe you have weird triangular cross sections. Maybe there's still circular cross sections, but they vary a little bit differently. So that's really going to be part of the problem that we have with these kinds of examples, is trying to figure out what the shape of this tank is and how that's going to impact the volume of the kth slice. Outside of that, I don't think there's really too much going on outside of maybe memorizing these formulas if you don't know them already. I think going back to this very beginning spot here is a helpful thing to see. Work is really force times distance. force is really mass times acceleration, and our acceleration here, if you're lifting upwards, is due to gravity. We know that mass is density times volume, so work is really density times volume times the acceleration due to gravity times our distance. Hopefully, that helps see how this integral formula really comes into play. That's all we've got for physical applications, or at least that's all my examples for physical applications. There are tons of other physical applications of integration that you can take a look through and see, but that's all I've got in this video.